Hello, thank you for coming to our CDR presentation. This is Group 2's presentation for Aerospace Design 1. Next slide, please. Just a brief introduction of our members. My name is Matthew Estenos.
I'm Bilal Hassan.
Hello, I'm Joel Perez.
I'm Victoria Merchant.
Hello, I'm Willer Sanchez.
Hello, I'm Christian Edgar.
Hello, I'm Zachary Acid.
And I'm Lauren Nowicki.
Next slide, please. I'll start off with a brief overview of our mission. So our mission is called DIRT, which stands for Drag-Inducing Regolith Transport. Now, our mission involves delivering an exploration excursion vehicle from Earth to a 5-sol circular parking orbit around Mars. So once we're in this parking orbit, our EEV will rendezvous with the Deep Space Transport, or DST, in this parking orbit. And then the crew for our EEV will be transferred from the DST into the EEV. At this point, the EEV will then leave the DST and perform a sortie to visit the 2 Martian moons, first Deimos and then Phobos, and finally return to the DST. So we have 2 primary experiments or collections on the 2 moons, and we'll be doing it on each of the 2 moons. So the first is to collect samples of regolith, or the dirt on the surface of the moons. Sort of the rationale behind this is that there's been some interest and some conceptual research into the use of this regolith as an air braking medium for future missions to Mars, which we're looking to support with this mission. So the general concept is, in a future mission to Mars, a spacecraft would stop at these moons, collect the regolith, and then continue on to Mars. And once they begin their descent into the Martian atmosphere, they would sort of spray this regolith ahead of the spacecraft, which would cause more drag on the spacecraft, which would more quickly lower the energy of the spacecraft, lower its orbital radius, and in general, cause a more efficient descent down to the surface of Mars. So we're collecting this regolith during this mission to be brought back to Earth and studied for this purpose. Our secondary mission is to measure surface radiation on the moons to inform future manned missions that could involve long-term stays or EVAs. Next slide, please. So this is our exploration excursion vehicle that we designed. We'll talk about it a bit more later, but in general, it has a total mass of 11,673 kilograms, a height of 3.7 meters, a width of 3.9 meters, and a depth of 6.7 meters. Next slide, please. So I'll give a brief overview of our trajectory now. So we're going to perform a single sortie around Mars from the DST to Deimos to Phobos and back to the DST. And we'll be using Hohmann-like transfers to perform these maneuvers. It's estimated that the interplanetary transfer between Earth and Mars should take about 278 days, and the estimated sortie duration, so again, from the DST to the moons and back to the DST, should take about 9 days. It's estimated that the total impulse that the EEV will need to perform the maneuvers should be about 4.35 kilometers per second. Next slide, please. I'll now go over the general timeline of the mission. This timeline was determined using STK to decide when it was optimal to perform these Hohmann-like transfers to minimize the delta V in the impulse required and therefore the fuel. So we'll start on September 23rd, 2037 by launching from Earth on a SpaceX Starship launch vehicle. At this point in Earth orbit, the Starship will refuel, and we're giving it about a day to do so. And then on September 24th, it will perform a burn to escape the Earth. Next slide, please. It will then be on a heliocentric transfer to Mars and will arrive at Mars on June 28th, 2038. Next slide, please. Upon arriving at Mars, it'll burn into its 5-sol parking orbit, at which point it will wait until January 1st, 2040 to rendezvous with the deep space transport. Next slide, please. After this rendezvous, the crew will be transferred from the DST to the EEV, and all of the important life support and other power systems of the EEV will be switched back on to prepare for the mission. And that will take place until January 3rd, 2040. Next slide, please. On January 3rd, the EEV will leave the DST and begin its transfer to the first moon, Deimos, and it will rendezvous with the first moon and land on January 4th, 2040. Next slide, please. So then once it is on Deimos, the EEV will be performing its sample collection and radiation measurement mission from January 4th to January 7th. Next slide, please. Then on January 7th, the EEV will leave Deimos, perform its transfer to Phobos, and land on Phobos, all on January 7th. Next slide, please. Then from January 7th to January 8th, it will perform a similar radiation measurement and regolith sample collection mission on Phobos. Next slide, please. Then on January 8th, the EEV will leave Phobos and begin its transfer back to the DST, where it will arrive at the DST on January 9th, therefore completing our mission. Next slide, please. There were several trade studies that were performed when determining the mission trajectory. One, of course, was what type of transfers we would be performing, either Hohmann-like transfers or bi-elliptic transfers. You can see from this data that this is a graph where the y-axis represents normalized impulse that is required. So it's sort of a measure of efficiency of the maneuvers. On the x-axis is a ratio. That is the ratio of the final and initial orbital radii of each orbit. So the final and initial orbit that you're transferring between. So basically we calculated this R parameter, this ratio for each of the transfers within our trajectory. And then we found that the highest one was just over 6 in terms of this ratio. So you can see the red dotted vertical line represents that. So that means all of our transfers lie either on that red vertical line or to the left of it. And we can see in that region, the Hohmann type transfer is the most efficient. That's why we'll be performing Hohmann type transfers. Next slide, please. The other major trade-off studies were related to the actual itinerary of the mission. Firstly, being the visitation order. So whether we were going to visit Deimos or Phobos first in the mission. This decision was made based on the concept of an abort trajectory. So what if during the mission there is some sort of failure in the engine? It does not produce the same efficiency that it needs to reach both moons, and it can only reach one moon, and then we need to get the EEV back to the DST safely for the sake of the crew. In this case, we decided that the moon we should visit should be the moon that requires the least impulse and therefore the least fuel to make a round trip to and from. So basically as sort of a factor of safety, the most likely chance that we'd be able to get the astronauts back safely with all that uncertainty and what's going on with the engines. So we performed the calculations. We found that it would be less expensive in terms of fuel and delta V to visit Deimos first rather than Phobos first. So that's why we're visiting Deimos first. The other major trade study was whether or not to perform an intermediate DST return. So whether to return to the DST in between Phobos and Deimos. We made this decision based on 2 parameters. The first being how it would affect the sortie duration. The second being the total EEV impulse. So we want to minimize the sortie duration because that means we would need to pack less consumables and less life support related things and decrease the mass that way if we minimize that. And then minimizing the EEV impulse would allow us to minimize fuel and the associated mass and cost. We found that by not performing a DST return in between the 2 moons, we would be able to significantly minimize both of these parameters. So that is why we are not performing an intermediate DST return. Next slide, please.
For propulsion technology, we chose chemical. Chemical offers a higher thrust than electrical, and it's simpler than nuclear, which requires larger tanks and advanced radiation shielding. The propulsion systems that we're using are the main propulsion system, which will be used for our launch stages, the orbital maneuvering system, which will be used for our delta V maneuvers, and the reaction control system, which will be used for our attitude and translational control. Next slide, please. For our main propulsion system, we're using the SpaceX Starship as our launch vehicle. The reusability of both the Starship and the Super Heavy booster provides a very low launch cost of approximately $2 million. And it has a large payload to Mars of 100,000 plus kilograms, which is why we chose it over the other launch systems that are in the table below. Next slide, please. For our orbital maneuvering system, we chose a chemical hypergolic bipropellant of MMH and NTO. The hypergolic bipropellants provide higher specific impulse than monopropellants and are simpler and smaller than cryogenic tanks due to the higher densities of monomethylhydrazine and nitrogen tetroxide. Hypergolic propellants can also self-ignite in space. And the propellant delivery system that we chose is pressure fed due to the compatibility with the RCS system for our shared tanks. The engine we chose is the RD0242M1, which has a specific impulse of 342 seconds and a thrust of 98.1 kilonewtons, which provides us a thrust to weight ratio of 0.2. Compared to other engines, it had a very high specific impulse for chemical hypergolic bipropellants and a high thrust, which the specific impulse gave us a low wet to wet to dry mass ratio of 3.64. Next slide.
Our reaction control system will use the R4D11 engine. This is a modern variant of the R4D engines used on the Apollo program. This will be using a set of 4 quadrilateral mini thrusters on the periphery of the EEV, and it will allow us to control the orientation and attitude of the EEV during orbital trajectories and sample collection. Our propulsion system or our propellant system is the same as the orbital maneuvering system, combined with it so that we can reduce the overall system complexity. And we chose hypergolic propellant for the same reason, to reduce the complexity of the design, as we wouldn't need igniters to ignite the propellant. Next slide, please.
And for life support and crew accommodations, we'll start with the cabin atmosphere. For the cabin atmosphere, we have 3 cryogenic tanks, 2 for oxygen and 1 for nitrogen, which will be used to keep a gaseous makeup within the cabin of 21% oxygen, 79% nitrogen, similar to that of Earth. Oxygen is obviously for the respiration for the astronauts, but it will also be for the fuel cell supply. And the nitrogen is just supplemental, and it's to avoid a completely oxygen environment, because a completely oxygen environment will introduce toxicity to the astronauts and fire hazards, which can be seen in this image of the Apollo 1 disaster. Next slide, please. Continuing with the cabin atmosphere, we have carbon dioxide removal. For carbon dioxide removal, we chose lithium hydroxide canisters. Within these canisters, there's obviously lithium hydroxide to absorb the CO2, but there's also activated charcoal for odor absorption, which is beneficial. And due to the relatively short duration of the mission, an open loop system of using these canisters until they're full and then having to replace them is justifiable. Next slide, please. And then we have pressure control. Pressure control is very straightforward. The cabin pressure will be monitored, and then the tanks of oxygen and nitrogen will be used to keep the pressure at around 1 to 1.3 kilopascals. And gas leaking is inevitable, so pressure changes are natural, and we will need to use these tanks to make sure that the pressure stays within our range. Next slide, please. And then we have ventilation. Air cannot stand still on the EEV. What will happen if the air stands still is that the CO2 that the astronauts exhale will surround their heads, and so they won't get the oxygen they need for respiration. And the equipment that we're going to be using, such as the heat exchangers, need air to flow through them. So a system of fans will be included for ventilation. Next slide, please. Temperature and humidity control will be controlled by the condensing heat exchanger. The condensing heat exchangers monitors any changes to both temperature and humidity, and it's designed to realign those changes to keep them within those ranges that you see here on this slide. Next slide, please. And for water, we have an originally full water tank on the EEV, so when the astronauts begin their mission, they have water that they can use. And then that water tank will be kept full from the byproduct of the proton exchange membrane fuel cells that we'll be using for power. And these fuel cells are so efficient that there's going to be excess water. So this excess water will just be disposed of off the EEV. And this water tank is sized so that it's enough water for the 2 crew for 2 days, which is long enough to get back to the DST in case of any emergencies at anywhere during the mission. Next slide, please. And then we have food. There will be enough food for the 2 astronauts to have 3 meals a day for 15 days. And you need waste disposal with food. So we have the universal waste management system that will be used for the safe disposal of human waste. And it's worth noting that the water reclamation components aren't necessary due to the amount of water that these fuel cells are going to be supplying. So what the universal waste management system is going to do is temporarily store the waste away from the astronauts and then periodically empty it into space during the mission. Next slide, please.
So for thermal control, we calculated our thermal loads using estimated efficiencies based on our research and the power consumption for each system to get the amount of thermal load the system expels. And once we had these thermal loads, in order to size each of our thermal control system components, we used the methods and elements of spacecraft design to get mass, area, volume, and all that good stuff. So for our efficiencies, our batteries are about 0.7. Ventilation is about 0.75. Fuel cells are 0.6, which is on the high end for a fuel cell, and all our other electronics are at 0.9 efficiency. And in terms of our thermal loads, most of the systems we looked at were relatively insignificant. Our largest thermal loads come from our fuel cells, which have about 4,600 watts of heat transferred, and our batteries, which have about 1,200 watts of heat transferred. In terms of our passive thermal control system, we selected a coating of MLI, multi-layer insulation. It's about 10 millimeters thick and 20 layers within that are allowed. And it's an extremely efficient insulator. That's one reason we picked it compared to silica aerogel, around 2 orders of magnitude less of heat transfer for the same thickness. And it's a very effective material for radiation protection as well. And only around 2 to the negative 16th millirads of radiation will be absorbed throughout the mission, which will be quite insignificant. We also installed 2 sided radiators, 2 of them, flush the EEV for active control system. They're both around 3.5 by 2 meters, and with both sides around 28 meters squared of total surface area for the radiators to do their job of expelling heat. We also have 2 shell and tube heat exchangers. One is the cabin heat exchanger that Zach talked about earlier, and the other is a heat exchanger installed with the fuel cells to help mitigate the heat from them. And they're about length diameter ratio of 5 and around 15 to 20 centimeter diameter heat exchangers. We also have a cubic heat pump for the entire EV, a cold plate specifically for our electronics. That's around 25 by 30 by 1 centimeter, and additional plumbing within the capsule of the EV. And these systems are going to need controls to ensure their work, and several fluids for the pump, for the heat exchangers, for our radiators. So we took into account the mass of those as well. And as you can see, for our systems, most of the mass comes from our radiators. Together, they're around 150 kilograms. They cost around $170,000. Most of the other systems have much more insignificant mass. Our heat exchangers both cost around $80,000. So those are pretty significant cost-wise. Our total cost is around $500,000 for all of these systems together, and our unit mass is 377 kilograms for all these systems. In terms of telecommunication, we selected the deep space optical communication system, and it's a future technology that's being tested right now, but should be available within the time frame of now and the mission. We compared it to a similar performance RF system, found that it's about half as massive, or not even 29 kilograms of mass, less than 100 watts compared to 120 watts for the RF system, and 200 gigabytes per second, much more significant than the RF system of 5 gigabytes per second. This system was designed to work for deep space, and it's being tested in the Psyche mission, which is being around asteroid 16 far away. So it's very suitable for our applications.
At critical points of our mission, we will require the EEV to dock with the DST. The method of docking we use is adopted from the International Docking System Standard provided by the ISS. We also use a soft capture system that reduces the impact and secures the EEV to the DST. It's depicted in the image on the bottom right of the screen. We also dock autonomously using a TRIDAR, which consists of a 3D camera and a laser control system. Next slide, please. In order to choose our main power source, we decided to perform a trade study. This trade study was from solar energy, fuel cells, and radiothermal generators. We found that the disadvantages for photovoltaics or solar energy was their diminished efficacy in deep space applications, especially in the scope of our mission since we're moving away from the sun. The large mass from solar arrays also proved to be a disadvantage. For radiothermal generators, the hazardous radiation emission is proven to be lethal to the astronauts on board. And we chose fuel cells because of their water waste product and low operating temperature. Next slide, please. The proton exchange membrane fuel cell is derived from the Apollo and Space Shuttle fuel cells. The total power production coming from this fuel cell is 4,600 watts and its life cycle is 208 days. We also use a secondary battery, a lithium ion battery, for instantaneous power for whenever we need it during the mission. The total power production coming from that is 4,096 watts with a life cycle of 10 years. The total operating cost of these systems is $4,560,161 US, and the total available power is 8,696 watts. Next slide, please. The total power required for our EEV is 2006 watts. Most of it coming from our power system, life support, thermo, and guidance, navigation, control. Next slide, please.
The EEV was fully modeled in SOLIDWORKS. SOLIDWORKS was then used to determine the moment of inertia and center of mass. Next slide, please. The EEV is split into two main components, the crew module above and the storage bay. Contained within the crew module is the crew and any additional equipment required for life support. Stored below in the storage bay are the sample collectors and the engine. Next slide. Mounted to the exterior of the EEV are the fuel tanks, hydrogen tanks, and radiators. Attached to the fuel tanks are the reaction control system. Next slide. Held within the EEV crew module is pressure. It is pressurized, and here's an example of some of the equipment within it. Some of this equipment includes the pump control system. Next slide. Contained below in the storage bay are the oxygen tanks, fuel cells, and any additional equipment. Contained on the outside of the storage bay are the telecommunication apparatus and additional equipment required for scientific research. Next slide, please. The crew module is comprised of a semi-monocoque in design. Which is comprised of a skin, and skin is made out of 2219 aluminum alloy. It is welded together to create a pressure seal, and the stringers and frames made out of 2024 T3 aluminum. The frame and stringers are mechanically fastened together. This yields a total habitable volume of about 16 meters cubed. Next slide, please. The frame and stringers are assumed to be uniform in size throughout the entire frame. So analysis was then performed using hand calculations. Critical analyses were performed on the frame to assume that during launch, the frame would have a factor of safety of about 2, and when in space, an internal pressure of 1 atmosphere is maintained. A factor of safety on the frame was then assumed to be about 53, and longitudinal stress yielded a factor of safety of about 1200. Next slide, please. The outer shell encapsulates the frame and skin. The outer shell is made out of Kevlar and reinforced with aluminum. The exterior shell is then mechanically fastened to the frame. Next slide, please. COPV tanks are used to store any additional volumes, which include oxygen and nitrogen. The storage compartment below is made out of 2024 T3 aluminum. Next slide, please.
Our guidance navigation control system is used in 2 phases. For the orbital trajectories phase, it is used to correct small perturbations in orbital trajectories using our RCS thrusters. Also, it's used to track position with our telecommunication system via the Deep Space Network. And we use AutoNav to reduce the error of the IMU by tracking the position of asteroids, known asteroids. Next slide, please. In the second phase, during sample collection, the GNC system is used to ensure safe landing on the regolith surface. So for this, we're using the EAS4700 integrated attitude and determination control system. This is an integrated unit, so it reduces the level of complexity and design required for our manufacturing. And in addition, for safe regolith, for hazard avoidance during the regolith landing, we're using a combined LiDAR system. This will ultimately be used to reduce the IMU error significantly and also assist the autonomous landing of the EEV. Finally, the MARDI camera will be used to visualize the sample collection for the astronauts on board. Next slide, please. So the entry, descent, and landing of the EEV is done in several stages based on the altitude of the EEV. Starting with at T-minus 20 kilometers, the laser altimeter activates to collect altitude data and reduce the IMU error from on the order of kilometers to about 100 kilometers, or meters, excuse me. The flash LiDAR then engages with terrain recognition mode to match contours with a known map and further reduce this error from 100 meters to about 10 meters. Finally, the Doppler LiDAR will collect precision velocity and altitude data at about T minus 2.5 kilometers to reduce the error to about a meter. At about T minus 1 kilometer, the flash LiDAR then narrows its field of vision and starts detecting for rocks, contours on the surface of the regolith, and craters. And this locates the appropriate landing site that the RCS thrusters are able to control and orientate the RCS to the safe landing site. At T minus 100 meters, as the EEV approaches the surface, it will fire its OMS engine to have a slow descent burn to slow the EEV for landing. After sample collection, it fires once more to ascend from the surface and continue the mission. Next slide, please.
All right, and I'm going to cover a bit more about the sample collection. So the provided mission guidelines had several requirements pertaining to the sample collection process. A sample of 50 kilograms must be collected from both Phobos and Deimos, and then quarantined and transported back to the DST. The sample mass was converted to an estimated sample volume using density values from type C asteroids, which are very similar in composition to both moons. Next slide. There are 5 sample material types that are recognized, but for this mission, we will be focusing on regolith collection, primarily for air braking research. Next slide. So our team examined multiple different possible mechanisms for the sample collection. The auger drill and coring idea was largely ruled out due to how slow the process would be and the opposing thrusts that would need to be expelled. The pneumatic sampler concept was ruled out largely due to the amount of nitrogen that would need to be transported for it to work properly. The clamshell skip design concept was settled on because it can collect both regolith and float samples and is able to collect the entire sample in one go. Next slide. Our design consists of 2 clamshell buckets with rigid digging teeth, as you can see in the image to the right, which shows our finalized design. This design is capable of handling a sample volume that is a factor of safety above the calculated required volume size. This mechanism is operated with a linear actuator, which will be manually initiated by the crew members on board the EEV, and you can see an image of this in action at the bottom of the slide. Next slide, please. The sampling mechanism will be manufactured using 7075 T6 aluminum to balance weight and structural integrity, and a linear actuator will be a size 11 series 28000 hybrid double stack. Next slide, please. About surface mobility, the collection process will be performed as a landed mission from the EEV in a determined collection zone using the LiDAR to map out the moon's surface. If there is some sort of issue with the desired landing area during the mission, then the RCS thrusters are capable of moving the EEV to a different site if needed. Next slide, please. Our mechanism will be self-quarantining in an effort to minimize cross-contamination where possible. Each clamshell bucket will completely isolate the respective sample, and after collection is complete, the mechanism will ascend into a sealed body compartment on the underside of the EEV, where it will remain for transport back to the DST. The images at the bottom of the slide show the final design for the isolation chambers where the samplers will quarantine. Next slide. The total cost of the mission was estimated at around $64,377,183. Each subsystem cost is listed in the table to show where that cost breakdown is coming from. And due to the reusability of Starship, the launch cost was kept relatively low. Next slide. And that concludes our presentation. Thank you for your time today. Are there any questions?
Thank you, great job. And thank you for finishing your presentation within 30 minutes. And let's ask the feedback suggestion quiz question from our audience first. Anybody has any question?
Yeah, so this is Rick Miles from Northrop Grumman. I'll take a stab here. Could you go to your cost slide?
Yeah, if you could pull that back up, Christian.
You need to share your screen.
My bad.
So this is just the vehicle itself. It's not having to go on to get there, right? This is just the machine itself that's 64 million.
Are you referring to launch?
Yeah, I mean, you said you're going to go board the SpaceX Starship, right?
Right,
Is that included in this cost here?
Yes, it's estimated right now to be approximately $2 million, considering reusability of both the Starship and the Super Heavy booster.
Okay. So you had $1 billion paycheck, right, from the government. And I've seen some other presentations where they totally went over the cost. So I'm curious as to, I just question that you're able to get the cost this low and leave what $900 million on the table. Seems like you could do certain things in order to improve the overall design with the pocketbook you've got, right? If you came to this with the customer, they'd say, okay, I'll take this as lowest cost option. Now show me that you can do it. And I think you would have a tough time building what you've proposed for this particular amount.
Let's see. Yeah, we actually agree. We think first off, a lot of the costs in like the research and development and also manufacturing is not included in this. So it'll definitely be blowing up or ballooning from that. In addition, the Starship costs are fairly, because it's not the design or actual flight tested vehicle yet. We're just quoting Elon Musk's pretty much quotations, and he said about $10 per kilogram, which even to us seemed unrealistic, but that's the cost that they're estimating based on a full Starship payload. So
right.
Yeah, even we agree that the cost is definitely gonna increase. And another thing is for a lot of the electronics, we were able to get everything else accurate, like for statistics like power, thermal, but cost is not something that's very like presented for these systems. So we did our best to estimate them.
Okay.
It's very likely that they're more. There were so many systems that we didn't feel like it would be a good idea to try to contact each of these manufacturers just for this project. So we 100% agree with you. The cost will increase.
Okay. And then I just have a little nit. If you could go to your thermal control slide. One more. Never present these many significant digits, right? You know, 7.2 repeating, 4.4 repeating, you know, just always think about your audience and try and present things very nice and crisp. I'm, you know, when I review reports, I'm never going to say something to that many significant digits, because typically I don't know it to that, so that you just round it off and move on, right?
Right.
Again, little nit, but it's important when you present stuff. When you present something with this many significant digits, that means you know it to that many significant digits. And I doubt that you can say that your heat from those different things are going to be specifically that many watts.
Got it. Thank you.
Mm-hmm.
Any other questions? Thank you for your suggestion and feedback. Any other question from our audience? Okay, so if no question from our audience, I will just comment on some of the slides. So first one, of course, as he just said, the significant digits, and it's not just these slides, and also on your I think it happened like 5 or 6 slides. You need try to fix that for in your final report. And let's talk about the structure part first. I think it's page 44. Yeah, so I think you show the result here. The frame is 2.5 4 millimeters thick and 4 rings with 6 ringers each. So I'm just wondering, like, what kind of stress analysis you did to have this conclusion?
So hand calcs were used for all of the structural analysis. So determine the, if you go to the next slide. Yeah, so determine the stresses. So for launching from Earth, we were assuming that we know that the mass of the EEV that was determined using SolidWorks, and then from SolidWorks, we were able to get our mass. The acceleration is known from Starship, records or their predictions. So then from there, we can determine our force. So some assumptions that we made regarding our calculations regarding launching from Earth are that the frame will, all of the force is being on the frame. The stringers and skin will not be receiving any of that force. So that is one of the assumptions we made. So then from there, to determine the forces on the frame, we made an assumption that the frame can be assumed as 2 vertical columns. And then there are a series of 4 columns, or there are a series of 4 rings on the frame, but each ring would be assumed to maintain that entire launch. So then it's just assumed that the stress, that the forces due to launch are 2 columns overall. And then from there, we were able to do a buckling analysis on that column. And using the provided design, we came to the assumption that there would be a factor of safety of about 2.17 regarding the design and the forces from launch on each frame. And then from there, we were able to do the internal pressure analysis. I'm sorry, what were you going to say?
Yeah, you can continue. Yeah.
Okay, so then we were able to do an internal pressure analysis as well. So some of the assumptions that we made regarding this analysis are that the skin, again, would not be receiving any of the force. It would all be maintained within the frame. However, this time it would be distributing the entire hoop strength, the entire hoop stress. So the stress from 1 atmosphere would be split across the 4 frames. And then, so that's how we came to the determination that there would be a factor of safety of about 53. Again, this is assuming that all of the frames and stringers are the same shape. And then some further assumptions that we made are that hoop stress is about half of that of the longitudinal stress. So the stringers, there are 6 stringers that are connecting each of the frames together. So we can make the assumption that there are 6 stringers across, even though there are 6 sets of 3 stringers making 18. We just assume that it's one long beam. And then, so the assumption that we made from that is that the longitudinal stress is half that of the hoop stress. And then there are 6 stringers. So that stress is further divided by 6 since it would be evenly distributed. So that yielded a factor of safety of about 1300.
So I was actually very surprised to see a safety factor like more than 1000. So you did all this analysis using SolidWorks?
No, these were all hand calculations.
Hand calculation, okay. My feeling is that there might be something wrong in your calculation.
Yeah.
It's unlikely that for this design, you have safety factor 2.117. Well, it's a little bit higher. We probably can lower a little bit to close to 1.5, but it's okay. It's not that horrible. But for a safety factor 53 and more than 1000, I would say you can definitely optimize your structure to make it lighter. And and let's say, let's assume that your calculation is correct. If the calculation is correct, you calculated the safety factor for stringer is much higher than frame, which means that if that is the situation, you can make your stringer much thinner. It does not need to be the same thickness as the frame.
And then a comment though is that the internal pressure calculations, those are directly correlated to the launch frames. So in order to get like a factor safety of 2 from launching from Earth, the factor safety of the internal pressure would also scale accordingly since they're both reliant upon the frame.
So I would suggest you to check that calculation in more detail. It might have some mistake.
Yeah.
Because the example I showed in the class, that one was a monocoque structure, and for that one calculated from like the load factor in the launch, and make sure that it does not buckling, and also we also consider in the deep space they have pressure difference and make it like your pressure vessel will not rupture. The calculated thickness, so they calculate thickness in the end. So the thickness is not that much difference.
Yeah.
and this one you calculate, wow, the safety factor is like so much different. So first check your calculation first, and then for if the safety factor is still too high, you can consider there should be some way to optimize your structure to make it lighter. It does not need to be so high. You can make it thinner, and the whole weight will decrease, the whole cost will decrease.
Okay, thank you.
Yeah. And for the power system, so I am kind of a little confused about the logic here. So you have the power system trade study, and you select the power system you want to use, and with all the parameters of the snagged power system, and then you have power distribution, and okay, this much power goes to this system, this much power goes to this system. I think a more reasonable logic is that first, I have the power budget. So this system requires this much power, and that system requires that much power, and I have a total power budget. And this is the total power we need to provide by our power system. And then based on that requirement, we design our power system, which power system we should select to have to satisfy that requirement with minimum weight, minimum cost, minimum volume, whatever. But this one, the logic I feel is that, okay, somehow you magically synergize some power system, and then you have the total power, and then you put that power to different power distribution to different system. So that's kind of my confusion part and my suggestion for the final report. And for the I think in the trade study of the launch vehicle on page 18, it's great that you have a trade study on launch vehicle, and you consider the cost, the payload, and how many launches it requires. They are all very important. One trivial thing you may consider to add here. Well, since you already snapped Starship, so it probably is not big deal because Starship is huge. But normally when we do the trade study for the launch vehicle, we need to consider that if your EEV can fit into the launch vehicle cargo bay. So we need to consider the height, the diameter. So that's just my suggestion is
I'll make sure to include that in the final report.
Yeah, thank you. And also for the on the next page. So Victoria, because the mic probably, I don't know, when you did the presentation, there was some noise. So I didn't hear it very clearly. You said on page 19, you selected the third one as your system and as your propulsion system, and then you said this will generate the thrust weight ratio. What's the magnitude?
The thrust to weight ratio of 0.2.
0.2. Okay. Okay. So that is the one that satisfies the requirement. Okay.
Yeah, I wanted to make sure to include that because in the presentation you said
Okay.
0.1 to 0.3.
And for the, let's see. I think the sure. Thank you, Matt. For the trajectory design, I think is as I commented in the PDR, it's really did very well. Everything is very clear, and all the information, the trade study, and the justification of like you even included the why we choose a home transfer as so I think everything did very well for the trajectory design, and I think that's pretty much it. Yeah, so I would say that overall great job. Just some small thing that you may consider put in your final report. They're not like criticizing or anything, just some suggestion. And any other question? Okay, so if no question, then congratulations, well done, and then work hard on the final report, and remember to send me the recorded video.
I will. Thank you, Dr.
Thank
Dong.
you.
Awesome. Thank you, Dr.
Thank you,
Dong.
Professor.
Thank you.
Have a
Thank
great
you.
day.
Thank you, everyone,
You're
for coming.
welcome.
Good work, guys.
Thank
you.
you.
Thank you.
Thank you, everyone.